And so the second part of the talk will be more about the Subrimanian spectral geometry, at least some questions in that. So before starting, again, I'm going to send the slides. There is lots of literature here. You can see that the one for spectral Subrimanian geometry, besides a couple of papers that I will mention later, is all in the last few years. And for general spectral geometry, which I'm going to mostly assume, besides telling you what are the main problems and the main ideas, the spectral geometry in the cloud seminar did a majestic thing. They made a nice list of very new references on different aspects of Subrimanian geometry, spectral geometry, and they made a nice page with hot open problems in spectral geometry. So I will just link that. The link was massive. I didn't want to write it down. Also, I made it tiny. But if you use those, you can actually find the reading material there. And so let's dive in. First part, I'm going to mention some bits and bits of spectral geometry. Who was at the GQT school has heard this part. And then I'm going to talk more about the equivalent of Laplace-Beltrami operator in Subrimanian geometry and a related problem of Subrimanian volume. So we'll basically get straight into open problems. I will use we'll use the Grushin problem that we have seen before as a motivating example for some of the answers that I'm going to give you. And then everything else will be we know nothing about it. So there will be a long list of open questions. So what is spectral geometry? This is something going back in the years, but you can say that it took, it started peaking with Weil, which was studying wave and it equation on domain and the real space. And when you study those problems, what you have some equation, and usually it boils down to some kind of diffusion equation. The easiest is the Laplacian, and then if you understand the Laplacian, you can bring bring the knowledge to study it and wave equations. And given that you are in a domain, so you're in a subset of the space, you need to explain how whatever you're studying inside this domain, its diffusion, wave, diffusion, whatever, how does that interact with the space? And so the boundary conditions are the way you encode the interaction with the space. What happens in this case of a domain in Rn is that you have countably many solutions of this equation, of the eigenvalue equation for the Laplacian, and they are ordered eigenvalue with one at the bottom that is always simple, and then many others that go to infinity. And what Weil did was, can we actually know something about this domain if we look at how many eigenvalues we have as we let lambda go into infinity? So if we start counting the eigenvalues and we count a lot of them, can this number tell us something about the domain? And it turns out that it can. So as lambda goes to infinity, the number of eigenvalues smaller than lambda tells you what is the volume of lambda, the area if you're in R2. It tells you what is the dimension of the space. It tells you what is the dimension of the boundary of this domain. It tells you what is the area of the boundary, or the length of the curve that encloses this boundary if you're in R2. And then if you actually go through, there are other terms that depend on the curvature of the boundary that I don't want to talk about now. So in the Euclidean case, there is some information about the domain that is encoded in the spectrum of the Laplacian. The Laplacian operator has a nice generalization in the context of Riemannian manifolds. And an old question by Mark Katz was, can we have the shape of a drum? So if we take a membrane on a curved space and we let it vibrate, so we are looking at the Laplace operator with the Dirichlet boundary condition at the boundary of the drum, can we actually say what drum did we have by just knowing the spectrum? What did it look like? And so what spectral geometry does, it takes a Riemannian manifold, And it wants to know what can you say about the geometry of the manifold by studying the spectrum of the Laplace-Beltrami operator, the divergence of the Laplacian, the divergence of the gradient, so the Laplacian on this manifold, when you put some boundary condition on the boundary, provided that the manifold has the boundary. If it doesn't, this doesn't matter. And the question was answered not long afterward. So what is not hard to prove is that if you have two isometric manifolds, they have the Laplace-Beltrami operators have the same spectrum. But what if I have two that have the same spectrum? Are going to be two isometric manifolds? And there is a simple Euclidean example. So if you take those two shapes and you compute the eigenvalues in both cases of Laplacian with Dirichlet boundary condition, they are isospectral and they are not isometric. So yeah, the opposite is not true, unfortunately, but can still we deduce something of the spectrum of those manifolds or of shapes? Can we deduce some geometrical properties of this shape by knowing the spectrum of the Laplacian? Turns out that we can. As we could detect the volume, the area, the volume of the set in the Euclidean space, we can detect the volume of the manifold, we can detect the dimension of the manifold, we can detect the dimension of this boundary if there is one. We can detect integrals of the scalar curvature over the manifold, and we can detect the genus of the manifold. We can detect lengths of closed geodesic. We can detect lots of stuff. So yes, isospectral manifolds are not isometric in general, but still the spectrum contains a lot of information. And we'll come back to this later. The other question is, say that we instead know what the geometry is. So we know a lot about our manifold. We know its structure. We know its deep, fine properties. Can we say something about the spectrum? Because that's very useful. It tells you, if you are looking at some experiment in physics, for example, what kind of energy you would need to study. But it can tell you properties of numbers if you look at modular surfaces and Laplacian of modular surfaces. So it has lots of implication and lots of fields that are theoretical, pure mathematics, and applied mathematics. So can we say something about that? Turns out that kind of, there are spectral inequalities and there are theories of minimizing manifolds that have been developed that work on these assumptions, and lots has been done. And yet it's still very open. Just as an example of what you can do if you have a non-compact manifold of finite volume, for example, modular surfaces, arithmetic surfaces, then there is the Cheeker constants that is an infimum over areas and volumes of open submanifolds that gives you a bound on the first eigenvalue. It tells you that it can't be smaller than that, so it gives you some rigidity there. And Busser inequality tells you that if you have lower bound on the Ricci curvature, then you have an upper bound in terms of the Ricci curvature and in terms of the Cheeker constant on the first eigenvalue. So it tells you that it's isolated and isolated in a very precise area of the space. So there is something there, and then there are lots of open questions on how big is the gap between the first and second eigenvalues, and what about the third, and how precise is the Weil law when you look at the spectrum? This is always bigger, always smaller. It becomes bigger at a certain point. That have various degree of importance in seemingly unrelated problems. So if you look at open questions in spectral geometry, you will see a lot about this. So this is our spectral geometry 101. We want to see what can we say about the manifold, or what can we say about the spectrum by knowing one or the other. So the question before doing anything is, can we do that in the Subrimanian geometry? And it tells us something. And before going in that direction, there is something I never mentioned during the talk. I said that in PDE's word, sub-elliptic operator and apoelliptic operator are essentially operators that arise in Subrimanian geometry. Now we are going to see that. And before doing that, I need to tell you what is an apoelliptic operator. So consider a second order linear differential operator. For example, the Laplacian. But take it general on Rn. So you will have some sums of second derivatives with some coefficient that possibly depends on the point. So this. Sums of first order terms that possibly depend on the points, and then a potential. This is, if you're doing physics, this d square over dxi square plus c of x, this would be a Schrödinger operator, modulo putting h bars around. And you take all this coefficient smooth. So an operator is apoelliptic if locally, so in all subset and for all distribution u, if locally the operator applied to u is C infinity, then it means that u is C infinity. And this locally is key. If something is local, there is very good chance that we can make sense of it in geometric terms. And what Ormander proved in the 67 is that if you have an apoelliptic operator, then its principal symbol, that is, you replace partial derivatives here with some number xij, xii, and if you want, you're replacing a vector field with a covector. You can think about that. So you're moving from the tangent to the cotangent space, if you want to think somewhat in geometric terms. Then the principal symbol, that is the first term, the one of higher order here, if your operator is apoelliptic, that thing is always non-negative. And then Ormander went on studying the Ormander types operators, that are operators that have exactly this form. They are sum of squares of these forms, plus a lower order term like this, plus C, but they did it in a very general setting. These are n vector fields over Rn, generic, whatever. They might be many more than the dimension, they might be less. You sum them up, you sum a first order term, or maybe that's 0, and then you sum a potential, and you want to know the properties of this operator. And the whole business of apoelliptic operator is about studying this kind of Ormander types operator. And you find that a lot of properties just depend on this principal symbol. And what is crucial is that Ormander also proved that if this set of vector fields that you're using here is bracket generating, the potential here doesn't play any role. If these vector fields are bracket generating, then the operator is apoelliptic. And now we are in business because we study distribution that are bracket generating. So we study sets of vector fields that we know have this property. And so we might as well study an operator that is given by the sum of the square of those vector fields. And what you do when you study apoelliptic operator manifolds or on submanifolds, that we will see, is exactly this. You're taking all this theory, you're saying it's local, it's very easy to make sense of it by something that goes from the tangent to the cotangent. It has exactly the structure that we have here, so we might as well study in our setting. So apoelliptic operators are something that is deeply connected to Subrimanian geometry, at least from a formal point of view of their definition. Before going there, let's remember how we define Laplace-Beltrami operator on Riemannian manifolds. So we have a Riemannian manifold, we have our manifold, we have the inner product on the tangent. We have a volume. Where does the volume come from? So we take an hyperparallel thing in the tangent, and we want the volume that takes this thing with sides of length 1 into volume 1. And this gives us the metric. I'll come back to it. It gives us the volume. I'll come back to that. And then we have a gradient here that is just that thing that when you apply to a function, and when you make a scalar product with a vector field, gives you the directional derivative. So if we think about the gradient, once we restrict x to a distribution, it seems that this makes sense. Shouldn't be such a big deal in the Subrimanian world. But then we have the divergence. The divergence is that thing that tells you how the volume is expanding or contracting as you flow on a vector field. At least that's one of the ways you can think about it. And this uses notion of volume. So to define the divergence, we need the volume. We need to keep that in mind. And then the Laplace-Beltrami is the divergence of the gradient. So we just plug in all the bits, and it does have a nice expression in terms of the metric. Are we all on the same page for now? I'm still on the Riemannian side. But so now we need to be careful because the Riemannian volume, as I was saying, is the volume of the parallelotope, it's called. Yeah, this hyperparallelo thing that I mentioned before. So I did write it down because the more I think about parallelotope, the more I forget about it's called. And so the Riemannian volume is deeply tied to the metric. And it's something that lives in the tangent bundle, but we are going to live in a subspace there. And yet we know that things can move everywhere in the tangent bundle. So this is going to create us problems. We don't have a very nice structure on the tangent bundle. And we know that to define Laplace-Beltrami operator, we need a volume because the divergence is defined in terms of a volume. So this is the first problem. The metric defined on the distribution has no canonical extension to the tangent bundle. And so we are stuck, at least a priori. What is the Subrimanian volume? And this is a real big question. There is a notion of volume that comes from the fact that we have a metric space. And this is something I didn't mention before. Opfrinov theorem holds in Subrimanian geometry. So if your submanifold as a metric space is complete, then it's complete geodesically in terms of the geodesic we define with respect to the distribution. So we still have this duality between metric spaces and geodesic spaces that you have in the Riemannian world. If one is complete as a geometric space with the geodesics, then it's complete as a metric space. So we can think, okay, let's change point of view. We go from our metric space approach to something that is, to our geometric approach to something that is more tied to metric spaces. And if we do that, we can make sense of a volume. There is this volume called the Ouster Volume. I thought I had written it down somewhere on my notes so that I could copy it when I was doing the seminar, but I'm gonna have to improvise. So what is this? This is the infimum of the sum of the diameters of the sets UI. Maybe there is a square I from 1 to some index n, such that the union of the UI contains your manifold. And so here you have H delta Q. And the diameter of the UI is smaller than delta. So you have a sequence of measure that that tells you basically what is the best covering of small ball that you can do of your set without making the sum of the diameter square blow up too much. And then you take the limit as delta goes to 0 of this thing and you get to a number. Sometimes. And this is your Ouster volume. And the spherical Ouster volume is the same, but instead of UI being generic open set, they are balls. So those two volumes have a meaning. They are well defined in the Subrimanian case. Except very few cases, nobody knows if they are even C1. And in our case, we need something that is C2. So this thing that I have defined here in a very badly approximated way, but it should be close enough to what they are defined, is not a very good measure to take, especially because it doesn't have the regularity property that we want. So we are stuck. The approach of using the metric space idea and doing Ouster volumes, by the way, these Ouster volumes are strictly related to the Ouster measure that we will come back later, that also are about how much stuff you need to cover your space when you make the covering finer and finer. So this is not a good choice. It might be regular enough, but nobody knows what regularity it is, so it's bad. There is another thing we could do. If we consider an equiregular manifold, an equiregular submanifold. So I told you that if they are equiregular, you have something. You have a nice Lie algebra structure that is defined over the graduation, the graded vector field over the distribution. You remember we had this chain d1 to the s, and we had that sum d1, d2 divided by d1, d3 plus d3 divided by d2, and so on. And I told you that if you are equiregular, you can actually make sense of that as a stratified Lie algebra. In that case, you can define something called an adapted frame. That is an orthonormal frame for your distribution, plus an ordered set of vector field that complete the frame for each of the bits. And in the case of a step 2, it means you have x1, xk are the one that span the distribution, xk plus 1, xn are orthonormal, we then expand the rest. The orthogonal space to your distribution, what's called sometimes the vertical space. And then you have some matrices that are defined in terms of brackets of those vector fields. And you can use those, and these are basically the gram matrices of the vectors of this frame. You can use those to define what is the volume of a parallelotope whose edges are element of this graded space. So you have the first k edges in the distribution, and you have found a canonical way to define the orthogonal space to the distribution and give an orthonormal basis there, and then you use those to define the frame. And it turns out, I mean, if you don't have the rest of the distribution, this is the same distribution you have in the same definition you have for a Riemannian volume, because you would just have x1, xk, and your manifold has dimension k, so it's just the volume of that parallelotope with the metric defining on the tangent bundle. But if you extend this definition with this adapted frame, and here there are some technicalities that I'm avoiding, but it's not too complicated as a definition, then it turns out that this definition does not depend on the frame that you have chosen for the orthogonal complement. So this actually makes sense. It's frame independent and is the same measure that you would have defined in the Riemannian case. So it looks like a natural extension of the Riemannian one. And if you want to be more precise on how you define this when you have this equiregular graded space, and I know this part is much more technical than most of the rest of the talk, but this is the only volume that makes sense for a large class of Subrimanian manifold that is known. So you, on each term of this graded, of this stratified algebra, you can, oops, I've deleted it instead of going with the point. You can define an inner product by using Lie brackets. And then you can bring the inner product on all these spaces in such a way that it respects this gradation. So from this, and the fact that you have a metric here and that you have Lie brackets, you can go to something that is defined on the wall graded space. And then you define a volume form on the dual of this thing. And then you want to transport this back to the tangent space, and it turns out that there is such a thing as a canonical isomorphism there. And this thing is exactly what gives you the pop volume. It's local, but if your manifold is orientable, then you can use the orientability to patch the wall space and glue all the things together. I don't want to go into more details on this. It's extremely well explained in both Ledonne's lecture notes, in the book by Agrachev, Barillari, Boscaini, in the paper where it was introduced. But when you look carefully at how it works, it's a natural extension on the construction you would have in the Riemannian case.
Marcello, just to clarify to see if I understand. So for instance, in the Heisenberg contact case, if you take like an orthonormal frame for the contact structure, yes, you would take the bracket of that frame, you would produce a third vector, and you would say that that one's unit length and like orthogonal to the other two? Yes. Is that what it does? Okay, okay.
Yes.
Then I'm happy, okay.
You use this to create an orthonormal basis like in a Grassmith-like way, and then say that that is length 1. And in fact, that matrices B that are replace the Gij in the formulas are exactly the Gram matrix for the choice you made of the vectors.
Okay, I understand. Thanks. Okay, that helps.
And it's a bit vague. If you want, we can come back to that, but I think it's extremely technical with respect to the level of everything else. So but what you're saying is exactly what is going on. And here they only use the fact that you can project from the cotangent to the tangent in the end. And that you have this Lie algebra structure that allows you to define canonically a complement for the distribution and to define an inner product there. As soon as you're not equiregular, this doesn't work. The alternative in non-equiregular case, in the case of almost Riemannian, I'm going to discuss in a bit. So for now, let's stick to equiregular. Then we have this volume that has been made because there is a lot of structure in the equiregular case. That is not that bad. It can be computed explicitly. Formulas are a bit long because it involves lots of terms, and you need to remember that you have that gradation, but it's something decent and it's smooth. And it corresponds to the...
Can I ask?
Yes.
Sorry, so you actually produce a Riemannian structure. So somehow, if you are an equiregular Subrimanian manifold, are you just a Riemannian manifold in disguise with some extra structure of this?
No, it's not. That's not exactly what you have, because if you look carefully, what happens is that it's no longer homogeneous. You have dilation that have that are non-homogeneous depending on where you are in the dilation. So if you do a dilation in the Riemannian case, you know you're locally Euclidean. So if you dilate by delta, all the terms in your neighborhood are multiplied by delta if you want, all the coordinates, right?
Mm-hmm.
Also, are you saying that the pop volume is like not it doesn't scale as the normal volume?
It doesn't scale homogeneously. It's not homogeneous.
Yeah, okay. I see.
The degree of non-homogeneity depends on where you are. So here you will have that your delta dilation, in fact, is delta to the power s when you look at the coordinates. So a box, when you dilate a box with sides of length 1, it will be stretched, and it will be stretched by delta square in the sides that are here, delta cube in the sides that are here, delta to the 4 in the one here, and delta to the s in the one that are here. So you are mimicking the structure, but the structure is essentially different. However, if you are on the Riemannian case, so if you didn't create this, if you didn't need to create this extension, and by the way, the deltas come because here you need to take commutators. So those deltas are multiplied. They are squared here because you have a commutator and you have delta appearing in both sides. Delta cube because you have 3 commutators. So the dilation on the vectors appears 3 times multiplied. And here appears s times multiplied. And so the fact that here you need to extend the inner product by using the commutator brings in this non-homogeneity of the space. It's a part of the construction there. And so you're cheating. You're making it look like as if you were in a Riemannian case, but you're very much not.
But then is this... oh, sorry, one last question, Marcel. But then is it true that this looks kind of like the Hausdorff volume? Like it scales in a kind of similar way as you would expect? Or?
Yes and no. In some cases where it's possible to do the Radon-Nikodym derivatives, yes, they are proportional. But in many cases, it's not possible to do that. So they are related, but their relation is complicated. That's what I wrote here.
That's really cool. Okay, thanks.
Go look at the paper on Grachev, Barilari, Boscaid 2012 about this stuff, and they study the relation between pop volume and Hausdorff volumes, especially the spherical one.
Yeah, thank you, Marcello.
Unfortunately, it's less trivial than one would like to have. So sometimes they are proportional, but don't bet on that. But at least pop is smooth, so we can use it to define Laplace-Beltrami operator. We have a smooth volume that can be written explicitly, that is not too bad, and that correspond to Riemannian volume if you are on a Riemannian manifold. So if your distribution is the tangent bundle. Other thing, if you define Subrimanian isometries, they preserve the pop volume. So it behaves nicely with isometries. And if they act transitively, then that's the only preserved volume. So it has lots of properties. There is a lot of rigidity around the pop volume. It's unfortunate that it's there only for equiregular, but it's, there is no way around it because that Lie algebra structure is essential and is there only for equiregular cases. There is a problem because it's unique when the isometries are transitive, but if something called nilpotent approximation, that is essentially this graded Lie algebra at different points are not isometric, then there are infinitely many pop volumes. So it's good, not always good, but at least it's good in a lot of cases. Other problem is in the 3D contact case, in a word that I'm going to mention later, the Weil law is studied. When you study the Weil law, you look at the asymptotic of the spectrum. And by doing that, you can look at how the density of the eigenfunctions of your operator evolve when the spectrum goes to infinity. And sometimes those things may have defined limit. So in the quantum ergodicity, what you say is that wave become random. The solution of your Laplace-Beltrami operator look more and more like a random wave if the underlying geodesic flow is ergodic. And then you have a limiting measure that comes from this, that is the Weil measure. What they proved is that if the rep flow is ergodic, then the measure tends to, then you have a quantum ergodicity and you have a limiting measure that is smooth and you could use for defining the Laplace-Beltrami, and it's not the pop measure. But there is at least another definition of measure. Issue. In the 3D contact case, as in the 4D quasi-contact case, you have normal forms. So you can use normal forms to define to work with micro-local analysis, and this gives you a lot of power. And those proofs, the one that I know about at least, they really rely on that. So this thing, for now, only exists in the 3D contact case, which is special anyway. There is a lot of work on curvature in the 3D contact case, for example, that does not work for other more complicated cases. But this tells you that there is a lot of uncertainty there. There are other measures that make sense, and they are new. People do not know yet how they are related and which one is the best one. The bet for now is that the pop one looks like a good choice in many cases. But it doesn't mean that it's the unique or the best choice always. And those are not necessarily all related. And if you are non-equiregular, then it's a wide open field as far as I know. So this is another big question in the Subrimanian work. What are the canonical volumes? Which one make more sense than the other? How do they differ from the volumes you have in Riemannian geometry? What different information they carry about the manifold and so on. So there is lots of research going on and there are not many answers yet. I mean, you have seen the one about the relation between Ouster volume and pop volume is 2012. The Weil measure is 2018. These are all very recent works. But now we have a volume. We know that we can define, at least in the equiregular case, a good volume. So we can take our Subrimanian manifold. We can take a bracket-generated distribution there of dimension k. We can take a smooth volume, anything. We don't have a canonical one we've seen, so we just pick one, as long as it's regular enough. We have a notion of horizontal gradient that is exactly the same as the gradient that we had in the Riemannian case, but it's restricted to the space that we know, to the distribution. So we see what happens on sections of the distribution, and that's what defines our gradient. And in fact, it's called horizontal gradient because it's really something on the horizontal space, the distribution. And then the divergence is going to have the same definition, but it's going to depend on some metric that is not necessarily the a canonical volume as in the Riemannian case. So for example, the pop volume, or maybe the Hausdorff one if you can prove that it's at least C2. Once you have that, then the sub-Laplacian has the same definition. It is the divergence of the gradient. Said in this term, it looks like it's an abstract object of which you can say very little about, but you can compute this thing in coordinates. And you can even start higher level, but you can compute it explicitly. So the gradient here, if you just project it on the basis of the distribution, this looks like it. It's just the directional derivative of a function times the vector of the derivative in that direction. So what it would look like in the Euclidean case, if you want, it's just it's on a weirder subspace of the tangent band. And the divergence is just a directional derivative. Well, the divergence of a product of a function and a vector is just directional derivative of the function and the functions then the divergence of the vector field. With those two properties that you obtain exactly the same way as the Riemannian case, you can explicitly compute what is the Laplacian of a function. And the Laplacian of a function is xi squared plus a terms of, here you have some coefficients and some order 1 operator. So this is really sum of xi squared plus x0. So we have suffered a lot of pain, but we can make sense of a sub-Laplacian. It's just that we need to define it for a generic smooth volume on the manifold, and we have to choose at this stage volume. We can't just go with the Riemannian. The pop volume is useful because what you can do is you can perturb your structure and have an epsilon perturbation that takes into account the rest of the distribution. And so you would have an actual Riemannian structure, and then in the limit, it would tend to the Subrimanian structure. And for irregular cases, then you would obtain the pop volume with that construction. And then you would take the sub-Laplacian like this for the pop volume. So there is some benefit in using the pop volume in this case, but you can't do it in general. So we have a Normander type operator. This one is bracket generating. So we know that this is an hypoelliptic operator, and hypoelliptic operators have lots of properties. So they are very nice operator to work with. And so we have our Laplacian. We can start looking at its basic properties. If we take the adjoint with respect to the L2 space with measure mu, then we find that we have a symmetric negative operator on a compactly supported function that for complete metric spaces, so if you look at MSR as a complete metric space, is actually essentially self-adjoint. Let me make a stop here. What does it mean to be essentially self-adjoint? If you go back to one of the first slides, I told you that boundary conditions are the way you tell how your system interacts with the environment. So if your manifold has a boundary, or if your domain has a boundary, it tells you what happens. Those are the boundary condition. At the boundary of your domain or of your manifold tell you what happens when you cross over. So how the waves interact with the exterior world. If you have a symmetric operator and you have a boundary, usually you need to impose boundary condition because you have many choices of how this operator can interact with the exterior world. And to make it self-adjoint, you need essentially to restrict the domain so that you have a well-defined unique closure. Boundary condition allow you to do that. There are some cases in which the structure of the system or the potential acting on the system, if we think about Schrödinger operators and Euclidean spaces, enforce a specific boundary condition. So you don't have a choice. The operator is already a self-adjoint and it has a unique closure, and this is a consequence of the structure of the operator and of the system. So you don't have to impose a boundary condition because there is a unique natural boundary condition that comes with the structure of the operator itself. This is what means essentially self-adjoint. The closure is exactly the operator that you were starting. There is just one closure of your operator. So when you have a complete metric space, the sub-Laplacian is essentially self-adjoint in L2 and its domain, so the space you start with that you have to complete is C0 infinity of M. And the heat operator, so the evolution of this flow, is a positive C infinity kernel and is a contractive semigroup. This opens a lot of questions about its content, its trace, relation with stochastic calculus and Malevich calculus. I'm not going into that, but you can do all this stuff because it's all well defined. So we have a symmetric negative operator that in some cases is essentially self-adjoint. Let's look at some example. If we are in a Riemannian case, this is the Laplace-Beltrami operator. It's well known for a complete Riemannian space, you have essentially self-adjoint Laplace-Beltrami operator for a geodesically complete one. In the Heisenberg case, your Laplacian is x1 squared plus x2 squared. Looks horrible, but it's something you can explicitly write down. And in fact, if you write down in terms of polar coordinate, it's not that horrible. You have a radius square appearing, you have a d theta there. So the angular momentum appearing, you have really what is the structure of a Laplace operator with the magnetic field here. And there is a strong relation between the two. I was mentioning it during the break and during the talk that there are people that study these examples because they want to study properties of magnetic Schrödinger operators. If we consider Grushin, this is almost Riemannian in the sense that it's a manifold that is Riemannian if you are away from the singular set, the one in which you lose one dimension in the distribution. Remember, the distribution is the span of the x and x dy. Because of this x, when x is 0, you lose this vector. So your distribution is two-dimensional when x is different from 0. As soon as x is 0, becomes one-dimensional. You have just the direction x. And then becomes two-dimensional again. And the in dy has a different weight depending how far away you are from the 0 axis. So outside of 0, this thing is two-dimensional. We are in a two-dimensional space. This is actually Riemannian. So we have a metric that we can adapt to this, the one that makes those vectors here unit vectors. So we take that as a natural metric because it's the natural metric outside of the singularity. Now we have a metric that is singular at 0. This blows up. Curvature here blows up when you get close to 0. Here you can define Gaussian curvature. You can see what happens. It's like 1 over absolute value of x squared. Blows up when you get close to 0, to x equals 0. And the Laplace-Beltrami, this is standard somewhat Laplace-Beltrami in the first term, even though there is this horrible rescaling in x. But as a first order term that is annoying, it's blowing up as well. This is something that does not happen in the equiregular case. In the equiregular case, you can drop this term and all the operator will look the same. It's just lower order correction to whatever you study. In the almost Riemannian, in which you can make sense of a canonical measure, yet the Subrimanian structure is bringing problems into the analysis. But you see, coming back to one of the questions is it something I can study as a master student? Those things are something you can write down as a master student, as a bachelor student. They are not intrinsically complicated. So you can make sense of the problem and you can go about studying them. It just, they are sometimes or often more complicated than the Euclidean counterpart. But you can get lots of insight from this. So let's look at this Grushin setting a bit more in detail. Before doing that, let me get back to the Hausdorff dimension, because this is now becoming essential. If you have a metric space, the Hausdorff dimension is telling you how many balls you need to cover your space, essentially. It's this limit here of balls that cover the boundary of your space. And there is a theorem called the Ball Box Theorem that allows you to control the size of Subrimanian ball in terms of non-homogeneous Euclidean boxes, the boxes that stretch that I was mentioning before. I don't want to go too much into the details, but by using this theorem, you can control the size of things, of the balls, in terms of the dilation coefficients. And those appear here. And then you find out that the absolute dimension is the sum of J, that is the where have you arrived in the gradation of your vector space, so at which step you are, times the difference of the dimension between your step and the step before. So if you take the case of the Dito problem, the first one would be 1, you have the dimension of the distribution that is 2, and then you have the dimension of the 0 that is 0, but then you have plus 2, and then you have the dimension of 3 minus 2, because you have the whole tangent space minus the distribution size. And so if you look at this, this is just 2 plus 2, and this is 4. And in fact, all the times this D is a proper subspace of the tangent bundle, then your Hausdorff dimension is going to be strictly larger than the dimension of the space. So in the contact case, the space is 3-dimensional, yet the Hausdorff dimension is 4-dimensional. In the quasi-contact case, you have 4-dimension, and the Hausdorff dimension is 5-dimensional. And thanks to that, to the Ball Box Theorem in equiregular case, at least for the equiregular case, that is still a large number of cases, it's actually easy to compute. Why did I bring it out is going to become clear soon, but this is something that we will need. So let's consider Grushin, and instead of a plane, we put it on a cylinder. So we are free to move in the x direction, but we have an angle in the y direction. So we are going to design a cylinder. This is the Riemannian matrix that makes these vectors unit vectors. And the geodesic flow, we can compute the Hamiltonian explicitly, that p times xi that we wrote in the last hour. And this is just px squared plus x squared p theta squared. You compute explicitly the equation of motion, you solve explicitly the equation of motion, you integrate them, and you can draw the geodesic flow of this thing. So it's not hard intrinsically to study this thing. This G, this is a Riemannian metric as long as you are in the complement of the singular set, the set in which you lose this, x equals 0. So outside this red line in the cylinder. And here we see one difference from what I told you before. I told you that all the complete metric spaces, all the complete Subrimanian spaces correspond to an essentially self-adjoint sublaplacian. But if you look here, once you remove the singular set, this is not geodesically complete. Geodesics, in the Grushin case, they start and they like to cross the singularity. So now we are left with the problem of studying a sublaplacian on a space in which the geodesic flow is not geodesically complete. Is it going to be essentially self-adjoint? Do we need boundary condition here? What can we say about this? Computing the sublaplacian in this case, we use the explicit formulas. It's very easy. It's just dx squared minus 1 over x dx plus x squared d theta squared. This is separable. This is, you can solve it actually explicitly. You can write the eigenfunction in terms of Bessel and hypergeometric functions. So it's beautifully simple to study. And that's the power of this simple example. You can do everything explicitly. You can compute the volume is going to be infinite. Unfortunately, it grows like 1 over x. You compute the curvature, you see that blows up. It's minus 2 over x squared. And so one has the right to question, okay, we have done so much effort and what we gained. Volume is infinite, curvature is blowing up. Does it even make sense to compute the Weyl law? Does it make sense to talk about curvature? In this case, yes, because you can talk about curvature in the Riemannian part. What it turns out is that on each of the half of the cylinder, so once you remove the singular set, each half cylinder, on each of the half cylinder, the Laplace-Beltrami operator is essentially self-adjoint. So those two parts of the space are completely independent from the Laplace-Beltrami point of view, even though geodesic flow crosses back and forth. And its spectrum is not just continuous spectrum of waves that goes to infinity, that go to infinity, scattering states they are called, but it contains embedded eigenvalues. So we can actually go and count the eigenvalues and see if they carry some information on the manifold. And if we go and compute that, what we find is that the first term, the one that usually measured the order of growth, the one that usually measured the dimension of the space, now measure the Hausdorff dimension of the space. If you compute this in the Martinet case, you will see lambda square. It's more clear if you look at the three-dimensional version of this. But you have something that now brings into the picture the Hausdorff dimension. It has some term that is unclear here, that is telling something maybe about the boundary or about the topology. And then it has some term that we will never find out because it's related to the Dirichlet counting function of multiples of prime divisors. So if you find out what term you have here, you have solved a big problem in number theory. But what this is telling us is that nevertheless, in this weird example in which everything is going wrong, it looks like we have some geometric information still hidden in the spectrum. And the Martinet case that you do this is exactly the same. You write explicitly. Martinet also can be solved explicitly in terms of special function, and then you find out that there is an embedded spectrum, and the counting function has this order here. So this was one of the first works in which we saw what was going on. And then this spawned the question, what happens in general? How general is the essential self-adjointness when you have don't have constant rank? So when you have this curve that change the size of your distribution, and how much information do you still carry from the spectrum? And in this setting, there has been recently a new paper announcing a conjecture already for the Riemannian case. So forget about the spectrum. Think about essential self-adjointness. I told you that a complete metric, a complete Riemannian manifold corresponds to an essentially self-adjoint Laplace-Beltrami operator. Coulomb-de-Verdier asked, if I have a closed, smooth manifold with a smooth density mu, and I take a formally self-adjoint differential operator there, is it true that the Hamiltonian flow of the symbol, so the Hamiltonian that corresponds to your operator, when you take the derivatives and you transform them into covectors, is it true that that Hamiltonian flow is complete if and only if the corresponding operator is essentially self-adjoint? This is open. It's true in some cases. If you have a Riemannian complete manifold, then it's essentially self-adjoint. If you look at first order operator on circles, then it's true. There are a few known cases, very few. In general, it's not known for a general formally self-adjoint differential operator, even of first order. And it's true, for example, for equiregular Subrimanian complete manifolds. So in a bit more general setting. It is false, we have seen, if you consider almost Riemannian manifold, like Grushin. Geodesic flow is non-complete, yet the Laplace-Beltrami is essentially self-adjoint. So this is a very non-trivial question. This is open, and this is not even Subrimanian geometry. This is open in standard differential geometry. So if you are expert of differential geometry, this might be a nice problem to look at, because if you find a counterexample, that's already a big thing. If you find a good set of examples, that's a very new thing. But let's go back now to the sub-Laplacians and the non-complete vector field. I've shown an example, but is it true in general? If I take a Subrimanian manifold that is complete and whose singular set does not have characteristic points, so this singular set is never tangent to the distribution. That's essential. We always can cross. We are never tangent to the distribution. And if you take a smooth measure on the manifold, but outside the singular set, like in the Grushin case, the full Grushin case is complete as a cylinder, but each half is not complete. And the metric makes sense only on each half, unfortunately. then what you find is that there is a functional inequality on the distance from the boundary. This gets tricky because it's the metric boundary and not the actual geometric boundary, and this thing makes sense. Okay, if you're not expert, close your ears. So this thing uses the metric closure of your metric space. So you will get a boundary even in things that are not even topological manifold. Think a cone, that would work. At the point, tip of the cone, you're joining two things. The point is not part of your manifold, is the singular set, yet you make the closure and you take the distance from that point, everything works, even though you are no longer in a geometric setting, but in a metric setting. So this thing uses that kind of technicalities behind. But so if you have a well-defined distance that is at least C2, and that satisfies this functional inequality, is Laplacian with respect to the smooth measure that you have decided, that you have picked, squared, plus the derivative of this Laplacian in the orthogonal to the boundary. Is a function that is greater or equal than 3/4 delta square minus some number k divided by delta. And if you have worked on Schrödinger operators, for example, Arnold-Bohm effects or point interaction, you might recognize this 3/4 over x squared. If this is satisfied, close by to the boundary, it's very local, it's just close by to the boundary. Everywhere else you can do whatever you want. But if this is true close by to the boundary, then the Laplace-Beltrami is with domain C0 infinity on the manifold without the singular curve. So on the cylinder without the red line is essentially self-adjoint. And is essentially self-adjoint in each of the connected components. So like in the cylinder, if this line cuts pieces of the space, those pieces of the space become independent, even though the geodesic flow crosses them all. So, and furthermore, if you have that your manifold without the singularity is relatively compact, then you have compactly solvers. So you can study Weil's law. So this string of self-adjointness is much more general than Drushin. And this is general enough that it brought new results in the Euclidean case, actually. But I'm not going into that. I just want to tell you what is behind the proof of this, just to give you a flavor of the kind of proofs that are there and the limitation of what we know. You proving that you have essential self-adjointness boils down to show that you have a nice normal tubular neighborhood of your singular set. So that around your singular set, you can flatten it, have a nice cylinder with a metric that is orthogonal to the singular set, and that behaves nicely in the other directions. And in particular, you want that this metric is goes like delta to the minus alpha for some alpha that is bigger than 1 when you move in the orthogonal direction, and is some smooth measure when you move in the tangent directions. If you have that, then you can replicate standard Euclidean proofs for self-adjointness. So you want an RD inequality, that is something that tells you that the quadratic form that defines your Laplace operator is bounded by some terms of the form 1 over delta square minus k over delta plus the norm of your function. This is very standard and very important inequality in analysis. When you have this, you know that your operator is semi-bounded. And this is where we really used all the structure about the tubular neighborhood. Once you have that, the job is almost done. Because once you have that, you can prove something that is called Abmont time estimate. It tells you that your wave functions, your solutions, have to decay very fast when you reach the boundary. And once you have that, there is a standard criteria for self-adjointness that tells you then you must be essentially self-adjoint. If you are semi-bounded, then you're essentially self-adjoint if and only if essentially you have an Abmont type estimate. So this part here is standard. This part here is a standard statement, but is where all the geometry is hidden. So we're understanding what the geodesic do very close to the boundary and how the space split and twists, there it's crucial. It's crucial to have this kind of inequality. So you mix up geometry and analysis when you start studying this kind of problems. And Problem is that there are many cases that do not fit this description. For example, in R2 still, you have a generalization of Martinet that is like the one that I've written here in the slides. And besides the case in which you have x times x squared plus y squared in y, that for its own reason can be treated, it's unknown if the operator is essentially self-adjoint. The hard inequality fails. There was a paper claiming that there is a sharp hard inequality, but Valentina Franceschi and Dario Brandi have a counterexample. So there was an error in the proof, unfortunately. The proof is true in a large amount of cases, but not in the generality that was there. So it's unknown if this thing is essentially self-adjoint. And the problem is that the metric does not have the structure of being delta to the minus alpha times smooth. There's this that creates this y square just destroys the whole argument. We couldn't figure out a way yet to make it work. This requires a new idea. You can't just use the two-color neighborhood. And it's a simple example. And even the simple explicit example of x to the power 4 plus y squared, we couldn't solve by n. So if somebody can, that's very good, already very good start. And there are more examples. This is, you have the in the x, and then you have something like Martinet again, the in the y times y minus x squared. In this case, you have one of those characteristic points. At the point 0, the singular set phi equals 0, that is a parabola, is tangent to the distribution. And again, self-adjointness is unknown. You have a symmetric Laplace-Beltrami, you compute it explicitly. I didn't do the explicit derivative in terms of y minus x squared because it would be long and wouldn't bring much more, but it's simple, it's explicit. We couldn't find an explicit way to say that it's essentially self-adjoint, and those are very simple examples. And if you look at the geodesics here, things are real weird. The distance, if you go away from the place the tangent structure is parallel, this goes like this modulus of square root of y minus absolute value. It's just horrible. There's this discontinuity on x equals 0. We can get RD type results here. Everything we tried fails here. We try to shrink the ball, take limiting approaches, look from inside, look from outside. I wish I would be able to prove that this thing is essentially self-adjoint. Everything makes me think that it should, but that point there, it's really nasty. And if you look at the geodesic flow is a nightmare. Look at the picture on the left. Look what kind of swirls start doing it. It becomes non-optimal as soon as it starts crossing the lines. Even though everything is explicit here, we can't read that. And it's a very simple example as well. So even just to figure out if your operator is self-adjoint and make sense of the spectrum, it's full of open questions there. Even in the Riemannian case, in the differential geometric case. So to go back to our original question, the Weil law in the Subrimanian case is mostly an open problem. In the equiregular case, where things are nice.
Marcello, maybe I would say like so because like we're more or less like on time.
Finished.
Yeah. So you have more. You need 5 more minutes or so.
Less, I think.
Okay. Perfect.
There is one older result that is Métivier in the 70s that proved that in the equiregular case you have half of the Ouster measure appearing there. There is our results on Grushin and Martinet in 2D. There is a result on 3D closed manifold by Colin-de-Verdier, where they do also the ergodicity of the rib flow, and they show that you have, again, Hausdorff dimension half, and here you have some weird quotient of the pop volume divided by a number. Quasi-contact case, the same. Hausdorff dimension, pop volume appear, but those two use normal forms that do not work in higher dimension. There is another work on singular Subrimanian manifold that tells that only can tell that there should be Hausdorff dimension appearing there, but they don't know what the terms are like. There should be new works by Colin-de-Verdier, Larret, Relat that tells more about more general picture, but this is really almost everything needs to be proven here. It's not know if the real periods are spectral invariant. Well, that thing would be the corresponding quantities in the Riemannian case are. So yeah, I wanted to talk about this because this is literally almost all open.